Hello and welcome to TidyX episode 17. All right, we're in the middle of our very angsty teenage episodes right now. My name's Ellis Hughes. I'm a statistical programmer at Fred Hutch Cancer Research Center. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward, and I do data analysis in sport. And you can find me at OSP Patrick on Twitter, and you can get to the both of us at tidy.explained@gmail.com. Or we love comments, and if you are watching the screencasts and you feel compelled to throw in a comment, thought, idea,
we love to hear them.
So.
Yeah, we'd love to hear them. We want to hear from our listeners. You know what you guys think, what you want us to do next. We're just enjoying doing this and putting this all together for y'all.
Yeah.
All right.
So what do we got today for our angsty teen years? I think we have comic book characters, which is perfect.
Yeah, exactly. So TidyX screencast where we go through and explain how our code works. We typically use Tidy Tuesday submissions, and this week's Tidy Tuesday submission is Uncanny X-men. So specifically, it's from the Claremont Run project. So this is organized, the Claremont Run, from what we've been able to gather, is from Chris Claremont's 16-year run of the Uncanny X-men. So he made a few hundred,
nearly 200 contributions,
and a number of comics, yeah. So to the X-Men story, and so somebody went through and pulled a bunch of information around all of these comic books, and put it into a data package. And so this past week, people went through, did a bunch of really fun visualizations, showing different ways that you could explore this data. But one that we thought was a lot of fun and we could go through and explore more was from Rebecca Stevick. Sorry if I mispronounced that name. But she made this really funny plot where she plotted the number of issues where the character flew versus the number of issues where that character hugged somebody, and actually drew a correlation between, if you fly, you probably hug people a lot, which, is a little bit ridiculous, but it's kind of fun.
Why wouldn't you?
Exactly. I mean, I think we should start hugging. Not right now.
No. It's COVID time.
But, hug some people when it's safe. Hug your family members when it's safe.
This is a nice plot. Because you know what it reminds me of, like an Excel type of plot where you get the regression line and you get the you put your little equation on there, and ironically enough, that this is the plot that we choose today, because I have a friend who's a exercise physiology scientist at a university, and he's trying to learn R, and he had sent me a message on Facebook and it was basically a plot like this. It was an Excel plot of some sort of physiological measure, and he said, it's killing me right now. Is there a way to do this in R? And I was like, well, it's pretty easy to do, and we're going to do it today. So here we go.
Sweet. All right, let's get this going. All right, so we talked to Rebecca. She said it was okay for us to go through her code. She posted the link here. So this is her Tidy Tuesday repository on GitHub. So we copied her code down and brought it into our R session here, running on RStudio. So the first thing that I wanted to bring up is she has a little bit of a header at the top of her R script. So this isn't an R markdown, which is typically what we suggest using, but she's using an R script to run all this, which is perfectly fine. But she has this header here at the top where she writes, this is what I'm doing, this is what the data is. But then she has this line here where she wrote when she last updated it. And so this can be captured fairly well if you're using version control like Git. But this is nice to have it within your file so that you don't have to go back and look at your Git logs to see what is updated. And so I know this is actually common practice where I work, is then if somebody comes back in and update it, then you add in, I updated it today. So today's the 5th, and here's what I updated. I can type. Here's what I updated. So that way, not only do we have a version control where we can track it, but we have it living within the file. So that's easy to track and go through. All right, so let's remove what I just did there. So first she loads in her libraries. So she's loading in Tidyverse for data manipulation, ggpub-r, which has some genome techniques that she ends up using to help create her plot. And then there's Harbor Themes, which is from Harbor Master. And he, created all these great themes and dumped them onto a package called Harbor Themes. Highly suggest using them. Harbor Master has some really great plots. All right. So after she loads, or let's load these libraries. I usually forget to do that. Next, she loads in the data using the slug. Just a reminder that Tidy Tuesday R is available on CRAN now, so you can go through and just load in the data by typing in the week of the data that you'd like to be pulling out and type in the year or the date that it was uploaded to GitHub. So let's load in the data using the slug, and then she starts going through and processing it. So first things first, she takes the characters data set, which is actually it's actually pretty long. It's 4,209 rows and 34 columns. So there's a fair amount of data in here. It looks a little bit sparse, just based off of this first little corner that I'm seeing here, where there's a lot of zeros. But what she goes through, she does a drop NA for flying with another character. So she's removing any cases where it's NA for the field flying with another character. So that entire row gets dropped. And then she groups by each character. So each character that exists in the character column. She then does a count on fly, or does a count based on the number of times they fly. Am I reading that properly?
Yeah, and she's the name there, right? If she did count fly, it would give a column name N, a lowercase n. So I think she's just renaming her column to say fly, because she's going to join that with a hug data set. And so if you were to just do the count, you'd have N and then N.2, I think, if you were to join those together, since it's a similar column.
Mm-hmm. Right, yeah. So she's just naming. Yeah, so if the character doesn't fly with another character, they drop the row, and then they count the number of times they go. Okay. Yeah, all right, she does that, and then she does the exact same sort of thing with hugging with another character. So she has 2 data frames right now, one of flying, so did the character fly or not with another character, and did they hug another character? All right, so then she goes through, and then she goes through to combine it together. So in this case, she uses a full join. So the full join is, it'll look, if you don't define the columns that you want it to be joining on, it'll look to see which column names exist in both, and then use that as the indices. And so in this case, she didn't define it, so it's going to use character. And then a full join is different from other joins, because in this case, it's going to keep all of the different characters that exist in either flying or hugging. If you were to be using a left join or a right join, a left join would keep only the characters that exist inside of the flying data set. Conversely, a right join would only keep all the characters that exist inside the hugging data set. But in this case, a full join joins all of them, but because of that, you end up with NAs, because if there's a character that exists inside of the hugging data set and not in the flying data set, there'll be an NA for hugging. And so what she does here is she goes through and replace NA and replace the hug column if it's NA with 0, same with fly. So now she ends up with a full data set where there's no NAs. And, for example, Angel never hugged anybody.
But did do some flying.
So it exists. Angel existed in the flying data set, not in the hug. So now they have a 0 there, and so that's what this is doing here. And then she goes through and plots it and generates plot. And we thought this was a pretty great way to create her cool visualization. So first thing, passes in the new flying hugging data set and sets her aesthetics that'll be used across all of the geoms where X is fly and Y is hug. And that adds in the points there. She defines the shape as 18, which I believe is a diamond shape. And then the size of 6. So then rather than them all being fairly small dots, she's making them like basically a font size 6. Like it's just making it larger.
Yeah.
And then she colors them whether the person hugged more than 20 times, and then sets them to be gray or royal blue. All right. So then she throws adds another layer, and this is a geom smooth. Patrick, do you maybe want to explain what's going on there?
Yeah, so this is the function that's going to produce the regression line that she had on the chart, on the figure. The method she sets to LM. So just by default in ggplot2, what you're going to get is you're going to get a lowest smoothing line, which is a locally weighted scatter plot smoothing line. So basically, you won't get a straight line like you would with a regression line. You'll get a like a linear regression line. You'll get a smooth line that, depending on how the points of the data look, is going to kind of perturbate up and down. So, for example, if you think about maybe like a parabolic curve or something like that, where it's or maybe data looks like an N or a U, it's going to be the line that kind of fits as many points as possible. So she specifies method equals LM to indicate that she wants a linear model for the line. She obviously gives it her color. Fill equals red 2, and then alpha gives some transparency to the fill, and the fill is specific to the confidence intervals that are going to surround that line. So geom smooth is always going to default to adding confidence intervals, no matter whether you're using the regression or the lowest smoother line. If you don't want them, you simply do SE, so that's for standard error. SE equals false, and that'll get rid of your confidence intervals.
But let's not put that in there. And then the next thing, actually, Patrick and I hadn't seen this before, but we both thought that was pretty cool. And this is how she added in the regression equation and correlation coefficients, is using these two geoms, or stats. I guess they're not labeled a geom. Stat regline equation and stat core. And so let's quickly bring up the help pages for those. Not regline equation. And so it does exactly what you'd expect it to do. Adds a regression line and an R squared on top of your ggplot. And so it's going to use the aesthetics that were already defined. So the x-axis, or the x being fly and y is hug, there. And then she defines, I believe label is the location.
Yep.
Yeah, so she defines the location that she wants this equation to exist. And the same sort of situation happens with stat core, where it's going to create a correlation, or calculate the correlation between the two items there, and then draw it at the specified location, and she specifies the color. So then she clearly had done a few iterations with this plot, because what she does here is that she adds it in these geom label and geom curves. And so we've used geom label a few times to label different points. And so what she did here is she labeled two different characters, Storm and Ariel Sprite Shadowcat. I'm guessing that's all the same person, just different superhero names.
Personality disorder.
Yeah. So she draws, she puts the name in, defining the alpha. So alpha is 0, so that would be fully clear.
It makes it super. The color she's using is a gray color, so she has that really, really dark black backdrop. So it's going to be a light gray, so it kind of pops a little bit.
Gotcha.
Yeah.
The H just is around that center point, how far to the left or the right. So H just 1 will shoot it all the way to the right of the point 24, 21. The vertical justification is 0.5, so she's going to move it half a point up. Sets a line height and colors. Then she does a geom curve, which is going to be drawing from the point where she has the label to the actual point of the dot, right? So that's a geom curve. She's setting the curvature to be negative 0.2, so that's normally just draw a straight line, and the curve is going to, if you do geom line, it would be a straight curve. The geom curve with the curvature is defining how much it's going to swoop between the two different points there. And then she's defining it to be an arrow, so then it's going to have the arrow pointing to the actual point there. She's defining the units of the arrow head here with the length equals unit 0.03 NPC. And the same sort of concept works here with Shadowcat. She adds her themes, the theme FTRC, which is from Harbor Master or Harbor Themes. She defines a few extra themes here, where she's setting the plot title text to be a size 20, the subtitle text to be royal blue, the x-axis title to be a size 14, but also bold. The same sort of situation with the y-axis. So she's making everything really bold and pop throughout this entire plot here, and then setting the plot caption to be a size 12. So it's a little bit smaller than the other ones. And then she adds her labels here, where the x-axis, the number of issues, y-axis, number of issues, x-axis, number of issues where the character flew, y-axis, number of characters where they hug, issues where they hug somebody, setting the title, the subtitle, and then, as always, the very important caption, which is kind of like your watermark, where she's saying where she gets her data from, and then she's adding, I made this for Tidy Tuesday, so, and then adding her Twitter handle in there. So let's run all that, and we get the same plot that she did.
There we go.
Ba-boom. All right, so she's got that genome smooth line there. She's coloring the two points that are above 20 hugs.
How come the regression equation is overlaying your correlation coefficient? And
I think that has to do with just the way that's visualizing. Like my computer is showing it.
Oh, it's not okay.
Yeah, I think
we didn't mess up the X and Y somehow.
Yeah,
no,
I think it's just the size. So she also. There we go. She also then saves it, so she's defining this width and height in DPI, and so I believe the positions that she placed these at and the sizes with this width and height,
that makes sense.
Will be based off of that, and so that's why it shows up so nice in her plot here. Without them overlapping, it's just simply because it doesn't automatically render them in that fine detail.
That's a good point. If you're going to be saving your plots, sometimes the way that you might specify them to look at them inside of R, or if you were to open them with Zoom or export them and copy and paste them as a JPEG, they might not always save looking like that. I know at work I've done a lot with SVG files and to put them into our own web page. And sometimes I have to specify them in kind of like a wonky way in the way they look in R, but when they get saved, they come out looking normal.
And, that's just like is iteration, and that's fine. That happens.
Exactly.
It's
a good point. It is a good point.
Yeah. All right. So we loved Rebecca's analysis. We thought it was a lot of fun. Comparing these two things that are clearly not correlated, or they're correlated, but it's not a causation. Just because you hug more people doesn't mean you're going to fly, right? Or just because you fly doesn't mean you're going to hug more people. So, but we loved this, and we wanted to continue this a little bit. And so what we wanted to do was generate a little bit of, take the linear regression and kind of explore that a little bit more in a few different ways. So Patrick put together this script here.
Yeah, so I thought it was pretty cool. I love the idea of her plotting the regression equation and the correlation coefficient directly onto the chart. Like we said, we had never seen those things, those functions, those stat functions that she had used. Normally, I would do this by just writing my regression equation, getting the coefficients, and then using the annotate function within ggplot. So since she didn't do the regression equation and plot it out, I decided we would do it here. So I built a regression equation using the same dependent and independent variables that she did. So the dependent variable of hug and the independent variable of fly. And we run that and we get our summary, our kind of disgusting looking summary output from R. We're going to show a different way of cleaning that up a bit. But you get some of the, you get the vitals, right? So you get the intercept and the coefficient for fly. So there we see 0.4364. So basically for every 1 unit increase of fly, we're increasing a 0.44 unit increase. We see a 0.44 unit increase in hug. And we get the standard errors around those coefficients, which can be used to calculate confidence intervals around those coefficients and give us a measure of uncertainty. And then from the t-value, we can also get our t-value in the standard error. We can get our p-values, which we see right there. And then at the bottom, we get some information about kind of how the model did. So we get the residual standard error is telling us about the standard deviations of the model errors. So how well model predicts relative to how many times the person actually did hug. And that's below that we get a multiple R squared and an adjusted R squared. So the multiple R squared and adjusted R squared. Basically what these are telling us, the R squared value is telling us is the percent of variability in the dependent variable that's being explained. And the adjustment to the R squared there is relative to the number of coefficients that are in the model. So if we were to add more coefficients besides just fly, this is a simple linear regression, but if we had like 5 coefficients, there'd be more of an adjustment to account for that. Mm-hmm. So basically what we're looking at here is, in general, this model is explaining about 25% of the variability that we see in hugs or hugging someone. Mm-hmm. And then we get information about the F statistic and the degrees of freedom, which help produce the p-value of this simple linear regression model. So that's a little bit about the regression. And then she also calculated correlation, which is basically a descriptive measure that tells us how 2 variables vary together, co-vary together linearly. And so we can easily run the core test function by passing it our 2 variables that we're interested in. Again, we get information about the data, about the model, so the t-value and the degrees of freedom and the p-value. Below that, we have our 95% confidence interval that surrounds the correlation coefficient. So even the correlation coefficient is 0.49, which we would think to be pretty moderate. We'd be kind of excited about that. Obviously, with such small data, 20 degrees of freedom and lots of variability in hugs and flying, you notice the 95% confidence intervals around that correlation coefficient are basically everything from pretty large, 0.76, to totally trivial and something we wouldn't probably get out of bed for at 0.09. So a lot of uncertainty. If we square that correlation coefficient, so here I put $estimate. So that pulls out the correlation estimate. And so I put $estimate. Yeah, if you do that and put names around X, so yeah, names, that's going to tell you all the potential things that we could pull out of this object. So if I just wanted, for example, the statistic, I could do $statistic, and that's going to give me the t-value that was produced from this model. Right. Yeah. So yeah, I pulled out the estimate and I square it. And what that does is it gives us our R squared, which is going to be about right around the same thing that we saw from our summary stat. Yeah, we got 2.4. And so that's pretty much what we end up with when we square our R squared value from just doing the normal correlation. And the other thing I wanted to show with this was actually if we took both variables and we z-scored them, since we're dealing with this simple linear correlation, if we z-score them and we run that linear model again, now we interpret the results on a standard deviation level. So basically what this is saying is it's saying for every 1 standard deviation increase in fly, we see a 0.49 standard deviation increase in hug. And you can tell that the R squareds don't change. It's not changing the model, but it's just changing the way that we interpret the coefficients. And now, because they're both on a z-scale, on a z-score, that fly z estimate, that fly z beta coefficient of 0.49, that's exactly, should be exactly the correlation coefficient that we calculated above when we did core test.
Interesting. Yeah. That's fun.
So that's a little bit about how kind of regression is working underneath this for the, there you go, 0.49. So
yeah.
But same value.
Same value.
So that's a little bit about how it's working under the hood. And then I said, well, why don't we make the table kind of nice? The output is a bit yucky. So there I go. I run the model again. That's kind of yucky. And so we did a few things here. The first is we load the broom package. And that's just a really convenient way. I think it was originally David Robinson who produced this, and now someone else has taken it over.
Thank you to whoever that is.
What's that?
Thank you to whoever that is.
No. This is a great package for dealing with models and extracting the key components in a very nice kind of way. Puts everything into a tibble. And then we'll load color table. I can't remember the guy's name who wrote that package.
I don't know. He's a schlub. He really doesn't.
No.
I wrote it.
Ellis wrote color table. So
Yeah.
this is a cool way of actually coloring your data outputs right there inside of R, and then obviously we load a knitter as well, which I don't think I needed.
Yeah, I don't think we actually end up using it.
I didn't use it. Yeah, but
Yeah,
so I build that model and I make this a nice tidy fit. So if we write fit table, you'll see the difference between this and the original model that we had run if we just do summary fit. Yeah, so this is going to produce a whole host of things, and if we run that fit table, we have kind of a much nicer TBL. Yep.
Yeah, so this is
Much
usually what
nicer
you're going to be caring about, right? Like when you do your regression, like you're caring more about, the table of the coefficients. That's what you're really usually trying to pull out of it. And, summary, it prints it out there, but you can't really pull it out. And then you've got to go into the guts of like, how do I pull all this out? And then it's different for each model. Each model type has a slightly different format of how you pull things out. And so the folks over at Broom have, spent a lot of time figuring out methods to pull it out for lots of different types of models. And so that's the real nice thing about Broom.
Yeah.
It does that.
And then the cool thing with this table is now we can actually color things using color table. So here, obviously we could have colored any of these things or created a different table if we wanted. Here I just said, okay, what if we cared about the p-value? And I said, I'm going to set styling. So mutate p-value is the column that I'm going to create. I'm going to set styling on the original p-value column. And I'm going to set this this sort of like if statement that says anytime the p-value is less than our arbitrary 0.05, no reason that can't be anything other than the fact that the stats gods once said 0.05 and everybody kind of stuck with it, which is probably a bad thing, but that's different. That's a different screencast. So I set it to 0.05. I said anytime it's below that, give it a background that's pale green, color the text black so that it kind of pops out, and set it to a style of bold. So make it nice and thick, and that's what we see down there in our output. So now we have a nice, cool kind of cool reading table, and we could write this out to a table that, in a markdown or something like that, or do other things. But that's a little bit about regression and using Broom and color table to get your information about your model and make it look pretty.
Yeah. Color table. I mean, I had a lot of fun writing it. It also will output to PDF, Word, HTML. If you want to using it in presentations for like HTML or LaTeX outputs, so it handles a bunch of different stuff. I wrote it because I was finding it really obnoxious to write different styling of colors based on the output that I'm wanting to do. So that's the benefit of that, in my opinion.
Cool.
Yeah, and then it also prints to console clearly, which I think is pretty cool. Awesome. So that was a little bit about linear regressions, and now we're going to continue that trend of going through your data, where we're going to use now the same data set. Let me quickly restart my R session. But Patrick wrote a fun little bit about k-means and PCA.
Yeah, and so we're going to kind of tie this together. Obviously, we did regression. We did a simple regression equation. Sometimes if you're dealing with a whole host of possible independent variables, sometimes it makes sense to parsimoniously reduce those down to more manageable chunks. And you can do that using the multi-collinearity between those variables using a PCA. And so we're gonna get into PCA in a second, but we're gonna back into it by first talking about k-means clustering. And so k-means clustering is an unsupervised learning technique where we're dealing with unlabeled data. So unlike the previous example where we had a specific dependent variable we were interested in, which was whether or not the person hugged other people frequently, this type of approach is going to say we don't have a dependent variable. We simply have unlabeled data. We have a whole set of features and variables, and what we want to do is we want to arrange these to find more similar people that are in one group, and that group should be a little bit different than another group, which contains other similar people, et cetera, et cetera. So we load in a bunch of functions here. at the top. I load in a few things. Tidyverse and TidyTuesdayR, obviously for data manipulation, and TidyTuesdayR to get the data. ggRepel we're going to use in our graphing, and then cluster and facto extra are simply packages that I loaded for the sole purpose of showing you some basic k-means clustering figures and why I don't like them, and then I'll show you how we use PCA to graph it in a more meaningful way. We set our theme to light because that's kind of what we always do. I wrote this little z-score function, which we're going to use in a second. So this is just going to calculate a standardized score, a z-score for us. And we're going to go ahead and load in our data. So there we have the X-Men data. Same data sets as before.
Yep.
I'm going to use the characters data set. And I just do a quick kind of separation. The characters were separated, or it was like characters equal and then their alias. So Wolverine equals Logan, for example. I'm just going to split those out so that we have two columns. And then visualization of X-Men characters, same kind of concept. Just create the separation between that column.
Just a quick glimpse to take a look at the data set that we got here.
Yep.
Check it's the same one that we looked at with Rebecca. Oh yeah, forgot to say thank you, Rebecca, for letting us go through your data or go through your code and explain how that all worked. I know that I learned a little bit there, and hopefully our listeners did too.
Yeah, for sure. So that cool. There's what our data looks like. So we've got everything kind of organized into those two data sets. So before I join them together, what I was going to do was do something very simple there. So these are just things that you can walk through, basically counts of how many times each character is appearing and things like that. Just some basic, simple stuff to look at. In the data aggregation piece here, what I'm going to do is I'm going to sum up several of these variables. So as the different characters are in the comic books, I'm summing up everything between speech and depicted, and I use across to do that. So I left the functions in. Most people don't. So I left the functions in so you could see exactly what I was doing. But within that across function, I do dot calls. So I want all the columns, including speech to depicted. And then for my functions, I just do a little list here, and I'm going to name the column. It's going to be tagged with the word total, and it's going to be the sum. And I did the list there because I wanted other types of functions. I could add comma and do a mean or a standard deviation or whatever it is that I'd like. So I do that on both of the data sets.
All right, so characters. So you were doing characters, you group by character, and the summarize across from rendering unconscious to clothing torn. Yep. Calculated the sum total there, so ran that for characters.
Yep,
and then you did...
Yep. Join them up.
Join them up with the inner join. So inner join is only going to keep characters that exist in both characters 2 and visualization 2, but that should be everybody, so we're not too worried about that.
So little exploratory data analysis. We don't have to plot all these. Obviously, if you're working through with the screencast with our GitHub, you can do that. The first one is a nice little plot that provides, X-Men provides lessons in life. And this one tells us that the more you talk, the higher your chance of being rendered unconscious. It's probably best to talk less and not be rendered unconscious. Obviously, Storm and Wolverine are characters that I think were mainstays during the Claremont Run. So, this data set and the way that I've organized it here is going to be highly confounded by the fact that the different characters who had the largest amount of opportunities or exposure are going to also come out on top in most of these variables. It might have been better to do it as a rate or something like that. But
number of times that they appear versus
exactly. Yeah.
But this is kind of fun. It's a healthy reminder to everybody. Talk less, you won't be knocked out.
Yeah, exactly. Exactly. So I look at that relationship in a few variables, and that's fine. We can go through that. You can work through them. They're all really basic stuff. This is also where I use the ggRepel. You can see the names of the people by each
Yeah.
by each of their points.
What it's trying to do is make sure that we don't have overlap of the labels.
Correct.
Which is what GG Repel does.
Yep.
Yeah. The author is super nice. I met him.
Yeah.
Yeah. Cool. So that's a couple different plots that you can go through.
A couple different plots. There's a base R plot here that'll plot all of the numeric variables for you. It's kind of messy when you have this many variables. I think it's, I don't love it, but
it exists.
Yeah, exactly. It's there if you want it. Okay, so based on all those 10 variables, let's do a little bit of clustering. So the first thing I do is I just normalize everything with that z-score function I wrote above the top. So obviously I'm removing the names. So now we're basically left with a data frame that is nothing but standardized scores.
Mm-hmm. So
there we go. Cool. The first thing we want to do is have an idea of how many clusters we need. There's a lot of different ways, or a number of different ways to figure out how many clusters you need. I'm just going to quickly use the elbow method here. So I'm going to write this little function that calculates the within sum of squares. So within cluster sum of squares. So basically I tell this function to go through a loop for every number from 1 to whatever I set the n clusters to, which in this case was 8 by 1. And it fits a k-means cluster based on each of those values. And then it stores or pulls out the within cluster sum of squares. And we can plot that, and we get a nice little what's called a scree plot. And there we go. Generally, for the elbow method, we're looking for the elbow of the plot. So we could probably stop at about 3. Maybe we can make an argument for 4, but basically you can see when we go from 1 cluster to 2, we get a very large drop in within cluster sum of squares. When we go to 2 to 3, we get another pretty decent drop. And then after that, by adding more clusters, we're not really improving our the variability, the within cluster sum of squares.
Mm-hmm. Yeah.
So we'll stick with 3 for this example. So I set the seed because k-means is going to always start in a random place. So I set the seed so that I can have repeatable results. And I tell it that I want 3 clusters, and we're going to run this all. And we get a bunch of information about the object that we called X-men clusters. Mm-hmm. And so, for example, this right there, those are the centroids, the center, the mean values for each of the cluster for each of the respective variables. So we can see cluster 1 really quickly. Again, these are standardized scores. So these are people who are probably in the comics a lot and are pretty busy when their character is written. They're doing lots of things. Cluster 3, conversely, is the opposite. These are probably people who are always negative, so their standardized score is always below 0. They're probably not people that are in the comic very much. And then cluster 2 is sort of the middle ground. And then below that, we get our vector of outcomes. So these are the clusters that the people are assigned to. We're going to use this in a second. Just be aware that you have to be certain, if you're going to pull this out and add it to your original data frame, that the ordering is the same. Mm-hmm. So if for whatever reason we change the order of the DF data frame, we would get in real trouble by trying to add these variables back into the data set, because we would be assigning the different characters to the incorrect cluster that they were found in the data. Mm-hmm. Just be sure of that. So we add it right there. We'll add them right in. Boom.
Boom. It exists. We have a cluster now.
And now we have a cluster. And so now with that, we can kind of look, and we can make a nice little table. So we'll use color table again. Forgot to load it. And we have a nice table. So we've colored them red, green, and blue for 3 clusters. And there we see red on top. So remember, cluster 1 was the people who were pretty active in each of the comics, and that was Wolverine and Storm, who we saw in our plots in our exploratory data analysis. Then we see some kind of like mainstay type of characters like Professor X and Nightcrawler and Cyclops and Rogue. And then below that are probably different characters that came in and out at at certain points across the Claremont Run, but weren't necessarily mainstays for the full thing.
Yeah.
Pretty nice. Mm-hmm. And then, so here's these are the two methods that we can use to just plot that R provides us. So the first one, FVIZ cluster. It's reasonable. You can see it's using ggplot2 in the backdrop. We can see the clusters, but we don't really know who's inside of those clusters. So it's kind of not really helping us a ton. The cluster plot, which is the next one, I think is actually even more challenging to work with. Again, we can see the clusters, but I don't really have a good feel. And this is only with, whatever it is, 20 characters or 22 characters. If we had hundreds of data points or hundreds of characters, it would be so sloppy to read this. Yeah. But the one thing that we can quickly notice is that this is plotting the clusters against principal component analysis. So you can see down at the bottom, it says these two components explain 84.79% of the point variability. And that the same thing was plotted on the previous graph, the one that was the FVIZ one. The same type of thing was plotted there. So there you go. If you sum up 74.4 and 10.4, you're getting about the same number. These are explaining the principal components. So why don't we build our own principal component analysis so that we can make a nicer plot? So that's what I do here. So I use there's I think 3 or 4 packages in R that do principal component analysis. In this case, I use the base function, which is printcomp. We run that over our standardized data. Remember, df+ was a standardized data set where we ran the z-scores on. And by clicking on summary there, we get information about the PCA. And then, yep, there we go. So we see right there, we see the proportion of variance each of these clusters explain, and then the cumulative proportion. So it took 10 principal components to explain 100% of the variability in our data. We can see that with principal components 1 and 2, as we saw in the k-means plots, we were explaining about 85% of the variability in the data. Mm-hmm. And then component 3, obviously all the way up, and it keeps accumulating until we get to 100% of the data.
Yeah, you're never gonna. When you're doing principal component analysis, you're actually never gonna end up with less principal components than fields of data that you pass into it, right? Mm-hmm. So like df+ has 10 columns.
Yeah.
Oh, not n. Ooh. Yeah.
Yep. There you go.
So you don't end up with less. So it's not reducing your data, but it's looking at the data in different ways.
Yeah, it's organizing the variables into clusters that allow for collinearity. So basically, the clusters are going to load certain variables that are more correlated with each other. And then the idea, there's different reasons why you would have orthogonal or non-orthogonal clusters, but generally, you'd have variables that are more clustered in comp 1, in comp 1 there, or in principal component 1, and then principal component 1 wouldn't be as correlated to principal component 2, but principal component 2 would have variables that are more correlated with each other. And then the amount of contribution that those variables are making to the components produce their weighting. So if we were to run this, look at the loadings. There we see, so principal component 1 obviously is using all 10 of our variables, and you can see the weightings. So everything is kind of contributing in a similar fashion, except for narrative total, right, which is really low. But then when you get to principal component 2, you see that narrative total is actually loaded extremely high, 0.8.
Just negative.
Just negative. And that's just because of the way that the variables line up. When we plot the biplot, you'll see that. But so it's loaded very high in that component there. So we can explain a lot of our variability in 2 principal components. We can actually use the component scores within a regression equation if we wanted to produce a regression equation of a whole bunch of variables that maybe have collinearity with each other, which would violate an assumption. If we were to use all 10 variables or 100 variables in a regression model, and many of them are correlated with each other, that's going to violate an assumption of regression. So one way to parsimoniously reduce that data down is to build a principal component analysis prior to. So the biplot is going to show us, we'll print the first two. By default, it will always print the first two principal components because those are the two principal components that explain the largest amount of variability in your data. And so you can see everything's loaded on principal component 1, moving left to right across the x-axis. Everything was positively loaded. You can see the variables going that way. And on principal component 2, you can see narrative is heavily loaded there. It's the one that's pointing nearly vertical down. So right there, you can see how that is loaded on the principal component 2, but you can see that it's least loaded on principal component 1 relative to the other variables. We could pull out as many different components as we want to make these kind of biplots. So this is components 2 and 3. So now we want to plot our kind of k-means clusters by using these principal components. So I take the component scores and I put them back into the data. Again, order matters. So if we, for some reason, change the original data frame order, we'd be in trouble here. And then I put those principal component scores back in. So that gives us a principal component score for each character. So there we see the component score for each character. So for example, if we look up at, like, let's say component 1. Okay.
Is that what you wanted?
The first character, whoever it was, in the data set, is going to have a, there you go, character.
We'll see. Because I accidentally ran it twice.
Oh.
All right, let me quickly run up and clean this up a little bit. So this is the danger. This is always why you want to be assigning to a new a new data set every time, so you don't accidentally
write over things.
But that was my fault, not Patrick's.
There we go. All right.
So there. Now we can do that. There we go.
Okay, so Angel, that perfect example. So when you take the weightings of principal component 1 and you apply them to her standardized score, her z-score for each of the 10 variables, and then sum them up, she's going to have a principal component 1 score of negative 2.1. She's one of the subjects, or the characters, subjects. One of the characters that are, we're not in research here.
No.
She's one of the characters that are in cluster 3, which is someone who's not very active within the comic books. Mm-hmm. So perfect. There you can see Wolverine and Storm at the bottom, 5s and 7s. So they're obviously very heavily loaded in component 1. So now we can use this information and plot principal component 1 and principal component 2 and use geom text repel to name them. And now we have a much cooler look at our data. So we can see all the way to the right, principal component 1 is consistent of Storm and Wolverine, who Wolverine is negative on comp 2, because remember comp 2 was heavily loaded on thought. So Wolverine talks a lot and fights a lot and he gets his clothes torn a lot, but he doesn't think a lot, which probably is why he gets rendered unconscious a lot. He talks, but he doesn't think. Talks before he thinks.
In line with the character.
In line with the character. In the middle there, we see principal component 2, which is the green group, and really cool kind of, you can see the distinction between the two components there. And then principal component 3, the characters who weren't in as frequently, you can see them kind of lined in right there, right around 0 on principal component 2, some negative, and then all of them are wholly negative on principal component 1.
Yep.
There we go.
And that's how you can do PCA, linear regression, clustering, combining all those things together for you, and then using color table to visualize it inside of the console as you go.
Make it look nice.
Yeah, there you go. But I think that's all we've got for you today. Hopefully you guys enjoyed it. Please leave any comments, thoughts, suggestions in the comments section, or find us on Twitter. Once again, my name's Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And you can find me at OSP Patrick. And you can hit up both of us at tidy.explained@gmail.com. Thanks a lot.
All right, thank you. Keep on exploring your world.